Good morning, students. In the last class, we had discussed about the potential due to a dipole, potential at a point due to a dipole. And in that class, in that lecture, I had told that we'll solve some numericals related to potential. So today, I'll solve some numericals. We'll together solve some numericals. And the first question here is, there's an electric field intensity at a point B due to a point charge Q kept at a point A is 24 Newton per Coulomb. So electric field intensity at point B due to a point charge Q kept at point A is 24 Newton per Coulomb, and electric potential at B due to the same charge is 12 joules per Coulomb. So calculate the distance AB and magnitude of the charge Q. So let us first understand the question. There are 2 points. Suppose this is A and this is B. At point A there is a point charge Q. Okay, and because of this point charge, the electric field intensity at this is 24 Newton per Coulomb. So given is E is equal to 24 Newton per Coulomb. Okay, and at the same point B, the potential due to this charge is 12 joules per Coulomb. So V is equal to 12 joules per Coulomb. What we need to calculate is this distance AB. I will say this is R and the magnitude of this charge Q. Okay, so the formula of E is 1 upon 4 pi epsilon naught Q upon R square, and formula of V is 1 upon 4 pi epsilon naught Q upon R. Now, if I divide this electric field intensity with the potential, which is here it is 24 newtons per Coulomb and this is 12 joules per Coulomb. If we divide E by V, E by V is equal to, if I divide it, what will remain is 1 upon 4 pi epsilon naught will cancel out, Q will cancel out, 1 R will cancel out. So 1 upon R is equal to 24 upon 12. 12 ones are 12 and 12 twos are 24. So what is the value of R here? 1 upon R is 2. So R is equal to 1 upon 2 meters or 0.5 meters. So this is the value of R. Okay. Now going forward, we have to calculate the value of Q. Now we can calculate it in the second step. Now what we have found out is R is equal to 0.5 meter. So we will put this value in one of these. Say suppose I will put it here. V is equal to 1 upon 4 pi epsilon naught Q upon R, that is 9 into 10 to the power 9 into Q upon 0.5. V is 12. So Q is equal to 6 upon 9 into 10 to the power 9 Yes. So this will be 2 by 3 into 10 to the power minus 9. Now you can calculate 2 by 3 is equal to 0.33 into 10 to the power minus 9. Q is Coulomb. So this is the, this is 0.67 into 10 to the power minus 9 Coulomb. So this is the answer. Value of the charge is 0.67 into 10 to the power minus 9 Coulomb. The value of distance between distance AB is 0.5 meters. So we'll go to the next question. Okay, the next question is, calculate the potential at a point P due to a charge of 4 into 10 to the power minus 7 Coulomb, which is located 9 centimeter away. And the part B of this question is, obtain the work done in bringing a charge of 2 into 10 to the power minus 9 Coulomb from infinity to that point. So first of all, what is given is, first of all, the potential due to the point. So the source charge value is given, Q is equal to 4 into 10 to the power minus 7 Coulomb, and the distance R is given 9 centimeter, which is 9 into 10 to the power minus 2 meters. We have to calculate the potential at point P. So potential at point P, if I write Vp is equal to 1 upon 4 pi epsilon naught Q upon R. So the value of 1 upon 4 pi epsilon naught is 9 into 10 to the power 9 into Q is 4 into 10 to the power minus 7 on R is 9 into 10 to the power minus 2. 9 and 9 will be cancelled out, and this will go up and become 11 minus 7. So 11 minus 7 is 10 to the power 4. So the answer is 4 into 10 to the power 4 volts. So the potential at point P is 4 into 10 to the power 4 volts. Now we have to calculate the work done. This is part A, which we have solved. Now part B, we have to calculate the work done in bringing up charge. See here, the charge here is Q1 is 2 into 10 to the power minus 9 Coulomb. So the formula work done is equal to Q into V. That means charge into the potential at that point is equal to the work done. So here work done will be, see, the charge here is 2 into 10 to the power minus 9 Coulomb, and potential is 4 into 10 to the power 4 volts. So this becomes 4 2s are 8 into 10 to the power minus 5 joules. So this is the work done. I hope you have understood these two parts of the question. Now let's go to the next question. Okay, the next question here is two metallic spheres of radius r and 2r are charged so that both of these have same surface charge density sigma. So if they are now connected to each other with a conducting wire, in which direction will the charge flow and why? So there are two spheres. A smaller sphere has a radius of r and the bigger sphere has a radius of 2r, and they are charged in such a manner that both of them have the same surface charge density sigma. So what if they are now connected with a conducting wire, what will be the direction of the flow of charge, and why does this charge flow? So this is a question. So let us first do some constructions, answer So there's one sphere. Let me draw a smaller sphere. Okay, and this has radius r, and there's a bigger sphere, and this has radius 2r. I will call inner sphere as A and outer sphere as B, and both of these have the same surface charge density. Both of these have same surface charge density. Okay, so what will be the amount of charge Q if there's a because of this surface charge density here the charge is Q1, and because of this surface charge density the charge is Q2. Suppose we say that like this. Now what is the surface area of a sphere? Surface area of a sphere, let us first write what is the formula for surface area of sphere is 4 pi r square. And what is the formula of the charge Q is equal to sigma into surface area. So let us calculate the first charge Q1. Q1 is equal to sigma, and the first surface area is sigma into 4 pi. First one is r square. Similarly, Q2 is sigma into 4 pi 2r square. So this becomes sigma into 4 pi into 4r square. Now I'll take a ratio of Q1 is to Q2. Let us take a ratio Q1 is to Q2. So sigma and sigma will cancel out, 4 pi and 4 pi will cancel out. R. So I'll write it down so that it will be easy for you to understand. Sigma 4 pi capital R square upon sigma 4 pi 4r square. So this cancels out. So here Q1 by Q2 is 1 upon 4. So this is, take this one relation. Now if I want to calculate potential at point at the center because of this sphere, suppose the potential of this sphere, it will be, suppose I will write it V1 is equal to 1 upon 4 pi epsilon naught Q1 upon R, and V2 is equal to 1 upon 4 pi epsilon naught Q2 upon 2R. Now I'll take the ratio of V1 is to V2. Again 1 upon 4 pi epsilon naught, both will cancel out. It will be Q1 upon R into 2R upon Q2. So R and R will cancel out, equal to V1 upon V2 is equal to Q1 Q2 multiplied by 2. From 1 Q1 upon Q2 is 1 upon 4. So V1 upon V2 is equal to 1 upon 4 into 2. 2 ones are 2 twos are. So V1 upon V2 is equal to 1 upon 2. That means V2 is equal to twice V1. From this we can infer that potential of the smaller sphere is lesser than the potential of the bigger sphere. This we can infer because V2 is greater than V1. V2 is twice of V1. That means the potential of the bigger sphere is more than the potential of the smaller sphere. So if we connect this with a conducting wire, the charge will flow from the body at a higher potential to the body at lower potential. So the charge will flow from the bigger sphere B to the smaller sphere A, and this is the answer. So this is it for today's class, and we will resume with the next class with the topic equipotential surfaces. Thank you.